Hi students, welcome to your third video for chapter 7. This time we're talking about nuclear reactions in particular. We define nuclear reactions as a process where an atom's nucleus changes by either gaining or releasing particles or energy. And in nuclear reactions, this process can release one, two, or all three types of particles as well as gamma rays. So think that it can release protons, neutrons, or electrons. Think back to the different types of radiation that we talked about, alpha, beta, and gamma. That covers the both there. There are two main types of nuclear reactions that we're going to be concerned with for this lesson. The first kind is known as nuclear fission. And so nuclear fission is defined as the splitting of one massive nucleus into two less massive nuclei, as well as subatomic particles and a massive amount of energy. The second kind that we're concerned with is nuclear fusion. Nuclear fusion is defined as two low mass nuclei which join together to create a more massive nuclei. And if you think about the root word here, fusion to fuse and fission to fissure. Fusion, fuse means come together. Fissure means splitting apart. And so just to review where we've been before, mainly we've talked about chemical reactions for the past few chapters, as I mentioned in previous videos, where atoms generally rearrange from the breaking and forming of chemical bonds. And really only electrons are involved. And relatively speaking, it only involves a small amount of energy released from the chemical equation. However, with nuclear reactions, it's a little bit different, where atoms change from one isotope into another, producing new elements altogether. Electrons, protons, and neutrons are all involved, and this involves the release of massive amounts of energy. And to understand the magnitude of where all this energy comes from, think of the equation E equals mc squared. This is Einstein's famous equation, one of the ones that made him quite famous, where energy is equal to mass times the speed of light squared. The speed of light is such a massive number that even with a small amount of mass, we can end up with a very large amount of energy. So nuclear reactions can occur under two different scenarios. One is naturally in nature, as we talked about with half-life, and of course, as we'll discuss a little bit later, what happens in stars. But another kind is induced nuclear reactions. Induced means forced. So we define these as forcing nuclear reactions to occur, often by what we say bombarding a nucleus with a subatomic alpha or beta particles or gamma rays. And so for example, here in this equation we have one helium alpha particle that's bombarding a nitrogen atom, and we end up with a nuclear reaction where now we have oxygen and hydrogen as the products. One thing that we can do with these induced nuclear reactions is, well, we can always write out the equation as if it was another chemical reaction. And so in this case, here we have our alpha particle with a mass of 4 and a atomic number of 2, plus our nitrogen, which has a mass of 14 and atomic number of 7 since it's nitrogen. And this translates into 17 as the mass for oxygen and 8 being our atomic number. And for hydrogen, we simply show it as a proton with a mass of 1 and an atomic number of 1, but we can use a symbol for proton here. Of course, we can also write it with the proper chemical symbols, and so we can put helium right here. Here's our nitrogen again. Oxygen's going to remain the same. And we could also put hydrogen here as well. Either way, you can use the proton symbol or hydrogen. We can use the alpha particle symbol or helium. It doesn't really make a difference. The one really important thing is that the numbers have to all add up. And so on this side, my mass is 18, and on my product side, the mass is also 18. On this side, I have 9 protons total combined, and on this side I also have 9 protons total combined. And that's really important. So one common example of nuclear fission is uranium-235, and this is what we actually have in the nuclear reactors here in Canada, such as the CANDU reactor. In order to induce a nuclear fission reaction with uranium-235, we actually bombard it with a neutron. And so combining a neutron with uranium-235 turns it into uranium-236, which is unstable. It simply can't have that many neutrons in the nucleus. So you can see there's the extra one right there. This leads to uranium-236 almost instantaneously splitting into 2 less massive nuclei. In this case, krypton-92 and barium-121. But if you do the math, 236 does not equal 92 plus 121. We're missing 3. And so the other thing that occurs is 3 neutrons are expelled when the nuclei split. And the other outcome from this on the product side is a massive amount of energy based on that E equals mc squared equation that we talked about before. As seen with the induced chemical reactions, it's an important skill to be able to write out the equations for these nuclear reactions. So in this case, to show the neutron, we're just going to put a small n. If you put big N, you might think it's nitrogen, so keep it as a small n. And if it has a mass of 1, but no protons, so we're going to put 0 there. We're going to add in our uranium-235, atomic number 92. We don't have to show the 236 in the equation, and so we can go right ahead and move to our krypton. So krypton 92, and its atomic number is 36, plus barium 121, with atomic number 56, plus this time we're going to have 3 as a coefficient, and then we'll show our neutrons there. And it's always good to say the energy is there as well. Writing out all these equations reminds me of that horrible chemistry joke. What do you do with a dead chemist? You bury him. One question that begs to be asked after we have our equation is, what happens to these 3 neutrons, especially if we're around a large source of uranium-235? If you think about it, it's probably quite rare for one single atom to be hanging out by itself. If this one neutron hits the uranium-235 atom, what do you think these 3 neutrons are going to do? Well, here's your answer. In this case, uranium-235 is going to undergo a chain reaction, where uranium-235, when bombarded with a neutron, is going to split into krypton-92 and barium-141. See, got it right this time. This is going to lead to 3 more neutrons being emitted. These 3 neutrons are each going to go and bombard a uranium-235 atom of their own. What happens after that? Well, you guessed it. It's going to split into barium-141 and krypton-92 again, each leaving 3 more neutrons out to hit more uranium-235. This process is going to occur again and again and again until all of the uranium-235 and neutrons have been used up. This occurs extremely quickly and releases an insanely ridiculous amount of energy. This is why nuclear reactions are so dangerous if they're not controlled, such as in atomic bombs. As mentioned before, there are 2 kinds of nuclear reactions. We've talked about the first kind, nuclear fission. Now it's time to talk about nuclear fusion. And this one is quite a lot more interesting, in my opinion. Nuclear fusion involves 2 low-mass nuclei joining together into one more massive nucleus. And this occurs in stars like our Sun. However, it requires insanely high pressure and ridiculously high temperatures in order to force these 2 low-mass isotopes together with enough force. The most common different isotopes that we see are different isotopes of hydrogen and helium in this process. We can write out these equations similar to how we wrote out nuclear fission equations. For example, here's an equation showing nuclear fission nuclear fusion of two different hydrogen isotopes. This is hydrogen 2 and hydrogen 3. Hydrogen 2 is known as deuterium, and hydrogen 3 is known as tritium. And when these form together, they end up as a helium nucleus and also a neutron as well. And you guessed it, there is also a massive amount of energy that is emitted from this equation. Again, if you look at the atomic masses or the mass numbers, they're the same on both sides, and the atomic numbers are the same on both sides. One thing that's really interesting with this is that all we're using is hydrogen, and we end up with something that's very harmless, helium. It's not a greenhouse gas. In fact, it doesn't really do much to the environment. And the other thing that we end up with is just a simple neutron. But the amount of energy that we get out of this matches the amount of energy that's in nuclear fission, such as in atomic bombs and nuclear generators. So the opportunity for nuclear fusion for powering our planet leads to three big questions. The first one, is there any way to actually harness fusion power to generate electricity here on Earth? Well, that's partially being answered right now. Around the world, there's a whole bunch of different research projects that are all very close to harnessing fusion energy, essentially building a sun inside a massive magnetic room. Of course, it's very complicated and very costly, but the benefit of it is essentially a lot of energy for next to nothing, because all we have to use is hydrogen. Nonetheless, if the development of the facility costs so much money, is this form of energy really worth our investment? Well, at this point we have to think of both the direct and indirect costs and benefits. Of course, it's so expensive up front. The research, paying all these nuclear physicists to actually come up with a sun inside a room, you can imagine that that is so pricey. But think about the indirect benefits, such as the benefit to the environment. If nuclear fusion can fuel our planet, think of all the coal mines and all the fossil fuels that we will no longer need for our energy requirements. And so that leads to the third question. How could nuclear fusion change our planet as we know it? Of course, we're still on the verge of seeing it actually captured and utilized to its full potential. But what could happen? Of course, that's up for your generation to decide. To finish off today's lesson, we'll compare nuclear fission and nuclear fusion as we've discussed it today. Nuclear fission reactions are when we have heavy and unstable nuclei split apart into two smaller nuclei. These unstable nuclei release a huge amount of energy when they split. The heavy nuclei will not release excess energy by splitting if they are as light as the element iron or lighter. Fission reactions often produce daughter products that are radioactive. This causes a radioactive waste problem for nuclear energy production, such as where do we store it and for how long. Many countries, including Canada, generate some of their electrical power through fusion reactions, such as the CANDU reactors in Ontario. Research does continue to try to produce environmentally friendly nuclear power generation. However, it is very tough because of the negative connotation of nuclear power. And a typical reaction down here, where we bombard an uranium-235 nucleus with a neutron, ending up with krypton-92, barium-141, and 3 neutrons, as well as a lot of energy. For fusion, we start with two lightweight nuclei, which join together to form a heavier nucleus. The lightweight nuclei release a huge amount of energy when they join. Lightweight nuclei will not release excess energy if the nucleus generated by fusing is heavier than iron, the opposite of fission. Fusion reactions often don't produce products that are radioactive. This makes nuclear fusion reactors an attractive possibility because they don't come with that whole waste problem of nuclear fission. Although there are no commercial fusion reactors in the world right now, this has changed since the date of print because there are several that are under construction. including one in France that is hoping to be open by 2020. Lastly, an equation of a typical fusion reaction, we have deuterium, hydrogen 2, and tritium, hydrogen 3, leading into helium plus a neutron and a massive amount of energy. This wraps up our lesson on nuclear fission and fusion. This sets us up for today's challenge, which is going to be researching for a debate which we'll have next week on the merits of nuclear energy and whether it's a viable option for energy needs in the future.